Okay, so here's an application which we can use first order ODEs to solve. We have a radioactive isotope, it has a half-life of 10 years. If the initial amount of the isotope is 1 gram, how much is left after 5 years? This was something I remember from, I guess, pre-calculus or algebra, and we could use just plain old pre-cal, I guess, to solve this. But the purpose is to show the difference equation that it comes from. So we have some amount, or the rate of change is some amount, which kind of harkens back to the Malthusian model, as a function of time, which is proportional to the amount that's there. And again, if I replace the symbol of proportionality with an equal sign, I'll add some constant of proportionality. And in a separable technique, I guess I'll write the A prime as dA by dt is equal to Ka, where I've dropped the independent variable t. And if I separate this thing out, I get dA over A is equal to K dt. And again, if I integrate both sides, I get the natural log of the magnitude of A is equal to KT plus some arbitrary constant C. And since we're dealing with an amount, the amount can never be negative, so I'll write this as the natural log of A is equal to KT plus C. And upon exponentiating on both sides, I'll get my function A of t is equal to e to the kt plus the constant c. And again, if I use some basic algebra, I could write this as e to the c times e to the kt, which I'll just declare as c1 e to the kt, since e to the c is just an arbitrary constant anyway. So as is typical in your algebra course, you may be given the formula A of t is equal to A naught e to the kt, where A naught is some initial amount. And so we're doing the same thing here, except we're actually proving this equation, if you will. Okay? Because we'll see now, if we go back to the problem, let's see, we have an initial amount of the isotope is 1 gram. So if I apply that initial condition, I have 1 gram is equal to C1 e to the 0, which is just 1. So my initial amount, of course, comes out anyway. So I get C1 is equal to 1, which is my initial amount. So I very well could have written this A is equal to A initial or A naught e to the kt. So anyway, my model now becomes A of t equals e to the kt. And it seems as if we need to be given just a little bit more information to find the rate of decay. So let's see. We have a radioactive isotope has a half-life of 10 years. That says that the total amount is going to be half of whatever the A naught is. So it's like saying A of t, which is going to end up being a half of A naught in this case. Or A is going to be, well, that's not going to be the function A of t, but it's going to be a half of A naught. So over here, I know that I started with 1 gram, so this just becomes half a gram is equal to 1 e to the k, and the time is 10 years, or the k times 10. So if I solve this, I take the natural log of both sides. Here I'll get the negative of the natural log of 2, which is the natural log of 1/2, which is the natural log of 1 minus the natural log of 2. ln1 is 0. Is equal to 10k, where k is a tenth of the natural log of 2. And I get that k is roughly a negative 0.0693, and so on and so forth. And we expect a negative rate. That's the only way we're going to have a decay process. Okay. Okay, so let's answer the question. I mean, now it's really just an algebra problem because we have a model that says A of t is equal to, well, A naught is 1 times e to the negative 0.0693, and I'll drop the rest and just put the t. Okay, just going after the idea and not, a very accurate number. So how much is going to be left after 5 years? Well, again, if I know an amount, I can find the time. If I know the time, I can find an amount. So here I know the time, I can find the amount after 5. So A 5, of course, is just going to be e to negative 0.0693 times 5. And I guess we can use any old calculator to figure out how much it would be after 5 years.